Come on, little buddy. There you go. All right, in theory, we're live. Do you remember when we didn't used to go live roughly close to the start time, Morgan?
Yeah, people have gotten so entitled, expectant to think that we could do this on time on a regular basis.
Yeah.
I mean, like 10 minutes late used to, and it was so much easier in the Google Hangouts days. Like we just literally would all be there, and then you press the one button that makes everything happen.
Yeah.
And yet now with all the technology, you're so much more polished about it.
Mm-hmm. Yep. Yeah. I start perfectly on time every time.
In summation, get off our lawn.
Kids these days.
Yeah.
Oh man.
Fraser was just reminiscing about his meetings with Tycho Brahe and the like before the show started.
That's right. Yeah. Yeah. Those were the good old days. Yeah. We were talking about how much the news has changed. And so when I started in 1999, it was like just after dark energy had been discovered. So just after we learned cosmology was completely wrong. But there actually hasn't been a lot of, I can't think of any big mysteries that have come out since dark energy. Like that's the last big one.
I don't think I've ever heard of a total overhaul of something in astronomy, at least not since I've been in the field.
Yeah. It's funny. Pamela and I talk about this every time we're getting ready, and people always ask us, like, can you do a show where you tell us how everything's different? And we have a really hard time thinking of like everything being different at a large scale. There's lots of really interesting incremental changes, but there aren't
It's
a lot.
not what every press release on Earth would have you believe.
Yeah, exactly.
I mean, the world has been revolutionized in the last 10 minutes.
Yeah, although I think we have one today. I was mentioning this as I was looking down the lineup today. I think we have a huge, just senses shattering redefinition of the solar system, which is pretty exciting. So I can't wait for us to get into that. I'm gonna say hi to people. Now I have all this time. I should just go back to my roots. Hello to Andrew Planet, Bob LeBlanc, Bob Moeller, Christian Woodland, David Fairweather, Froden Gautier, Gordon Dewis, Harry Patrick, Johnny J, Larry Beckham, Martin Bradshaw, Nancy Graziano, Raj Luthra, Rich Wilson, Arjone, Sir Goosey, Roger Haskins, Stephen Hawkins, Susan Hunter, Ted Krause, and Zappan Zappan. Hey everybody, welcome. Who else did I bit? Eamon Fanton. Yeah. Nancy's thinking that gravitational wave detection was rather earth-shattering and extraordinary. Was it? Or was it expected?
It wasn't a redefinition, but it was maybe the most impressive thing that's happened since Hubble finding the acceleration of the expansion.
I think of it like the Higgs field, the Higgs boson, right? Like we knew it was there, and it was just a matter of finding it.
Yeah, I guess I'm more impressed by gravitational waves than the Higgs boson.
Yeah.
So does it feel old? I mean, I grew up, I was born the year that the Voyager spacecraft was launched. So I got to watch, as a small boy, but the solar system was reinvented, rediscovered, with Voyager, all those beautiful images.
Well, nothing truly cool has happened since Voyager in planetary science. Like, New Horizons was as close as you got to like that sort of magical discovery feeling. Nothing as similar has happened since Voyager.
Yeah. We've seen Pluto for the first time up close.
Yeah, that was as close.
That was cool.
Yeah, all right, that's fine.
Oh, I mean, it was amazing, but yeah, that sense of like total, just like we have no idea what's coming from Voyager is just we've seen things now.
Yeah, that's true. Maybe Dawn, seeing Vesta and Ceres up close. We are kind of running out of worlds to see for the first time, though.
When we get to Titan, like when Dragonfly lands on Titan, I think that's going to be a holy cow.
Yeah,
because it's going to look unlike any. We've seen rocky things, and we've seen icy things, and we've seen hellscapes and all these things, but we've seen nothing. We haven't seen lakes and oceans in astronomy pictures, and I think that's going to just be arresting.
Yeah. Yeah, I can't wait. It's only 2035. I just got to stick with this for another, I don't know, 20 years or so.
Exoplanets, people with exoplanets in the chat, that's a good example too. Like we knew planets were out there, but finding them has just been amazing.
Yeah, 95. Yeah, 95. So that was before my time though. So we already knew. I was reporting on like the 10th planet when I started. I'm so old. Okay, let us begin. Let me put you all back into your boxes. Back to me. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, March 17th, 2021. I'm Fraser Kane, publisher of Universe Today. This week, no guest, lots of stories. We are going to be talking about stellar streams, a previously rediscovered meteor shower. Mars, where did Mars's water go? Measuring the smallest amount of gravity, detecting a black hole on the move, and what I'm calling the story of the year, the source of zodiacal light. Joining me on my screen right now, I've got Dr. Morgan Rayburn. Morgan.
Hey Fraser, we've got some good ones this week.
Yeah, it's good. It's good. I'm actually glad that we don't have time for guests.
It's gonna be a cracking episode.
Yeah. People were worried if we would be able to sort of fill the whole show without a guest, but in the past, just the two of us have filled an entire show. So
we're gonna have a good time.
Yeah, we'll be able to sort of run through this. Who else have we got? We got Moya McTeer. Hey, Moya.
Hi, Fraser. How's it going?
Good. And we've got Alan Versfeld. Hey, Alan.
Hey, nice to be here.
And as always, I've got to thank you for getting up at the crack of dawn, South African time. So thank you.
Well, it's fun.
That's fine. It's fine. You'll sleep when you're dead. All right.
Yeah.
Okay, so before we get into this week's stories, I just want to give, as always, a huge thank you to our good friends at the Weekly Space Hangout crew. They are our friends, our fans, our executive producers, and I don't say this lightly. I know I sound really flippant when I talk about this, but they are the people who organize the special guests. If you've ever wanted to call an astronaut and say, hey, can we interview you? This is your chance. So go to the wshcrew.space. They'll hook you up, give you your executive producer privileges, and embrace you with their incredible community and keep you entertained while we go on hiatus every summer. So, all right, let's get into this week's show. And I want to start with the big story. Moya.
Okay.
Yeah, let's do it.
I'm ready. I'm ready. So I had never heard of zodiacal light before I saw this story. So I'm coming at this with fresh eyes, and I hope that you all interject with extra information that I'm missing or extra context. So since I didn't know what zodiacal light was, I'm going to tell you about it. When you look at the sky, at the horizon, just before sunrise or after sunset, you'll see this diffuse, out of focus light at the horizon, and that is zodiacal light. We've known about it for a while. Some theories were that maybe it was leftover dust from the formation of the solar system. Maybe it was dust from asteroids and comets coming in. The way that it happens is that the sunlight gets bounced off of all of these dust grains in the space between planets. But now we know, based on observations and models, that it's probably Mars where this zodiacal light dust is coming from. And it was a chance. It was by chance that this happened. So the Juno spacecraft that was sent to study Jupiter, on its way, realized how do I want to say this? The person who designed the cameras for Jupiter put 4 cameras on it to take a lot of pictures so that it could compare its position on the sky by looking at pictures of stars and comparing it to known patterns of how the stars should look. But the person who designed it also wanted to be able to find transient events, so things that appear in one picture but disappear, and then we would be able to study them. And one of these transient events that happened was these streaks of dust that would appear in some images and then go away a few seconds later. They also noticed that there were a lot of dust grains hitting the solar panels and hitting the camera at really high speeds, at like 10,000 miles per hour, which is wild. And so they I guess didn't do much with that data for a while, and now they're studying it, or they were studying it, to see what where did these streaks of dust come from? And they noticed that the distribution of these dust grains was highest in the space between Earth and the asteroid belt. And when they studied it further, they saw that the dust grains really are localized to this annulus between Earth and Jupiter, centered around 2 AU from the sun. So really right where Mars is. And then when they came back to model the distribution of dust grains in the solar system, they found that if you start with the initial conditions of where Mars is and how what the dust grains would be made of, because we have sent rovers to Mars and now we know what the dust grains are made of, when you run those models, then it shows that the light that you can expect from that, the sunlight bouncing off those dust grains, does match the zodiacal light that we see. And so now we have empirical and model evidence that Mars is the origin of zodiacal light. And with this newfound precise distribution of dust grains in the interplanetary space, we can create or plan better spacefaring missions in the future so that they can avoid the worst of this dust, because the dust grains actually do really affect the spacecraft that go out there. They can, the article that I read said that they can chip off up to 1,000 times more mass from the spacecraft than the dust grains have themselves. Like, they are really damaging. And so now we can avoid them. And now we can plan and build spacecrafts that are better able to withstand that force.
And, I think, like, for a lot of, you as a professional astronomer, you as a data-oriented astronomer are less familiar with zodiacal light. But for the amateur astronomers, it's sort of on the list of targets that you go after with your setup. Like, you go to find a really nice dark sky setup just before dawn or just after sunset. And you take a nice long exposure, and if you play your cards right and the conditions are great, you get this beautiful shot of the zodiacal light. And the story had always been that it was, as you said, the leftover debris from the formation of the solar system, the ground up asteroids that had been bumping into each other. But when we discover this source that it's actually Mars, it has this totally different feeling. That is for me anyway, is that we're not looking at the remnants of the creation of the solar system. We're looking at the gasps of this dying planet that is blowing off this dust into space. This is what killed Spirit or Opportunity. Sorry,
maybe this is a dumb question. Did they say how the dust was getting off of Mars? Is this all ejecta from impacts?
They explicitly said that they don't know, and that they hope future studies find that out.
But I guess the inference here is that Mars would be the dominant source of interplanetary particles, at least in the inner solar system. And that's a pretty substantial claim, considering you have Mercury and the Moon also getting pelted by micrometeoroid impacts and diffusing things off into space. To say it's all coming from Mars and then sort of pushing inwards from the against the solar wind is I'm not doubting the modeling that they've done, but that's quite a substantial claim. It's not a surprise that it would be centered at, you said, 2 AU, which would be outside the orbit of Mars, where in general photon pressure of the light is pushing it out. But for it to get all the way in to create this zodiacal light that we're seeing.
Well, go ahead, Alan.
I was going to say, would that then be why we don't have something similar coming from the Moon and from Mercury?
They don't have planet-wide dust storms that kill our probes, right?
Right. So I was thinking of ejecta, because they'll have plenty of that.
Yeah, my inference, and I think it's important that Moya said that we don't know for sure the source. That it could be something that's older. It could have been, if Phobos and Deimos were created by an asteroid impact, that's what caused it. But I just sort of in my mind imagine, we know that the atmosphere of Mars has been blown away, although we're about to get, that's going to be a little more complicated today as well. But we know that the atmosphere of Mars has been blown away into space. And so we can imagine maybe the dust getting into the high atmosphere and making its way out out of the gravitational well of Mars and going into orbit around the sun as well.
This must be and I haven't read this paper, so I'm kind of asking questions in real time here. But the time scale for the solar wind to clear those kinds of microparticles out of the solar system is pretty short. It's not billions of years. So this dust can't have been from formation of Mars or something like that. It must be some source. And like you're saying with the dust storms, that's a plausible idea. There must be some source that is supplying and replenishing that dust. Otherwise, it would have been gone, billions of years ago.
Well, and I think there's
going to be Saturn's rings all over.
Yeah, it's an echo to Saturn's rings. And this is sort of in your, what are the mechanisms, Morgan, with Saturn?
Well, we think that the rings were once a lot heavier, and they've lost a lot of material. But we really don't have a mechanism. That's the problem. So let's talk about the situation that's most like this, which is the E-ring. That's the ring created by the geysers on Enceladus blasting particles out into space. We knew that there had to be those geysers because if you turn off that supply, you would blow the E-ring away because of the solar wind within 100 years or a few hundred years. So there had to be something that was keeping it going. Now, the rest of the rings are a different situation, and we now know that they're pretty young, hundreds of millions of years old, and we have basically no mechanism for how that's possible. And so there must be something that is either they were way heavier before and they've just been bleeding down, or they're being replenished somehow, and we don't really have an idea of what that could be.
Yeah. So it was funny. When I saw this story come across my desk, I was just like, what? No, this can't be. This is amazing. And I was all over it. It was just amazing. Alan, have you ever taken a picture of the zodiacal light? You've got nice dark skies there.
You'd think. No, we have lots of dark skies away from the cities, very far from the cities. We have areas like the Karoo Desert and so on, but they're hard to get to, and I've never made that much effort.
Yeah, there you go.
I know plenty of people who I know who have, but not me.
And one of the other things that's interesting, and maybe you reported on this, Morgan, a few months back, that New Horizons was able to take pictures while it was outside of the inner solar system and outside of this light pollution caused by the zodiacal light and other dust in the inner solar system. And so it's actually a fairly significant amount of material that blocks our view to the rest of the universe. It allowed us to recalculate the number of galaxies in the universe purely through New Horizons being outside of this wall of dust. So it seems like it's a lot more important than we had led to believe. It was sort of this adorable annoyance, and now it looks like it's, it grinds spacecraft, it indicates the suffering of planets, and it blocks our view to the cosmos and obscures our understanding of our place in the universe. Zodiacal light!
Gosh darn it, dust.
Yeah, exactly.
It had never occurred to me before that there was natural light pollution.
Yeah.
That's cool, and it sucks.
Well, people always ask me this question, would it make more sense to put a telescope out by the orbit of Neptune? And they're thinking, because then we would be closer, and then we could find Planet 9, because we'd be closer to Planet 9. And I say, well, half the time, sure, but also putting a telescope out to Neptune is hard. But now, thinking about this, maybe the answer is yes, that getting outside of the inner solar system actually makes a ton of sense for getting a nice pristine view of the cosmos outside of the dust that's blocking our view, that's hiding the truth for us.
There was a reason we were keeping Neptune around.
Exactly. All right. Excellent. Well, you're on my screen, Morgan. So why don't you tell us I hinted at the next big mystery that's been possibly not solved.
Yeah, this is not a solution. It's
No.
it's an idea, but let's keep that Mars theme going. So, thanks to the last 20 years of observing Mars, we've put together this kind of tidy picture where billions of years ago, sort of 3.5 to 4 billion years ago, Mars was a warm, wet place with a thick atmosphere, liquid water on the surface, potentially life. That's what Perseverance is looking for right now in one of these ancient river deltas. And then sort of over a pretty short period of time, that water went away, the planet cooled down, the atmosphere has been bleeding off, and now we're left with a planet that used to be much like Earth, is now sort of cold and dry and presumably dead. And basically the whole time, we've assumed that all of that water, all that atmosphere was being lost to space. And now there's a paper that came out this week in Nature that makes a different argument. And it's specifically about the water. And the idea is, instead of the water going up, maybe instead the water went down. And the idea here is a process that actually happens on Earth called crustal hydration. And the idea of crustal hydration is basically that water wears away at rocks, minerals, and things. And as it does that, it forms new minerals that incorporate molecules of water. We call those aqueous minerals. And every time you form an aqueous mineral, you're taking a drop of water out of the ocean and locking it up in the crust. And on Earth, that process happens, and that crust then gets subducted down through plate tectonics into the inside of the planet. And then it melts, and then that water ends up making its way back to the surface as the lubricant that helps lava flow during volcanoes. And so we're not really losing water in a net sense here on Earth. But Mars doesn't have plate tectonics. We don't really think that it ever did. And so it was more of a one-way journey is the argument that's being made here. That as these aqueous minerals were formed, they got basically piled up on the surface and never were able to be broken open and release those bits of water again. And this is supported by spacecraft observations, both orbiting spacecraft, but also the rovers and the landers. They've pretty much uniformly found evidence for aqueous minerals on Mars, and they're like basically everywhere. What we don't know is how deep that layer is, and that's kind of the key question. That's the trouble with remote sensing, is all you see is the tiniest veneer on the surface. And so it could be that there's a millimeter thick layer of aqueous minerals across the planet. That was like the last, as the oceans were drying up for the last bit, that's where it went. Or it could be that there's a kilometer of aqueous minerals on the surface. And we don't really have the tools to find out. There are a few things we can do, like look at fresh impact craters and try to see what material has been revealed. The rovers are able to, make observations on the surface that can't be made from space. And so this team from Caltech basically took all of that circumstantial evidence and tried to calculate the volume of aqueous minerals that might be on the surface. Wow. And then compare that to how much water we think maybe was on Mars early in its life. And I hope you're getting the sense here that there's a lot of ifs and maybes in this. We don't know how much water there was. We don't know how much aqueous minerals there might be today, but we can make educated guesses about both of those and then compare them. And when they do that, they found that potentially anywhere from a third to all of the water that might have been on Mars could have plausibly been incorporated into these aqueous minerals.
Wow.
And thus this crustal hydration could have been a principal driver for Mars losing its surface ocean. Now, I think nobody's arguing that it's 100%, even if the math might say it's possible. Certainly there's been water lost to space. And we know that there's some trapped in the polar ice caps and what have you. But I think there hadn't been a lot of serious consideration of the idea that a substantial fraction of the water actually migrated inwards. And this study is kind of arguing that maybe we should look at that again.
So, I mean, the traditional story, of course, is that the water evaporated from the surface of Mars, went up into the atmosphere, the sunlight broke it up into hydrogen, oxygen. The hydrogen atoms were blown out into space. The oxygen, I guess, helped to oxidize and rust the rocks and turn into the carbon dioxide that we see there today. But it is interesting, sort of this idea that Mars is so far and so cold that you would be getting this water sort of drying and evaporating and floating up into the atmosphere in large amounts. That this idea of it going into the rock actually makes a ton of sense.
Yeah, and this probably happened in phases. We have good evidence that there was water in local areas on Mars well after this sort of 3.5 to 4 billion year kind of heyday of the wet Mars. And so it could have happened in some areas, just like on Earth, the lithic geology, the makeup of the rocks in different parts of Mars is different. And so it would have incorporated water better in some areas and not so well in others. And so you could have had a situation where the parts where the rock was kind of a sponge for creating these aqueous minerals, this process happens relatively quickly. And then other places, it happens very slowly, and maybe so slowly that in those areas, lost space is the dominant effect.
Mm-hmm.
So, we don't really know. Obviously, the more data we can get, the better. So Perseverance is going to be able to, one of the great things Perseverance will be able to do is it's landed in this river delta, which has these sort of canyons, basically. It's like a canyon that it's driving into. And canyons are gold mines for geologists because they're like little time capsules showing you all the layers of history. And so hopefully Perseverance will be able to sort of study those layers and try to gauge what was going on and whether those processes would have been conducive to crustal hydration to sort of narrow down our bounds a little bit about what the plausible realm we're talking about is here.
So do you think that it could actually see layers of hydration in these sedimentary layers of the riverbed?
Potentially, like everything else, it's hard when you have what you see on the surface. And so, if this process happened 4 billion years ago, well, there's been a lot of weathering that happens just like here on Earth of those rocks. And so you have new chemical reactions that are happening on that thin layer. Now, Perseverance carries lasers that are designed to bore and burn off those top layers, as well as drills to try to go into those areas. And it's just a question of whether they'll happen to be able to drill an area that's conducive to that, rather than just individual rocks that are laying like on the ground, which will be, less helpful probably than being able to, like if you were a human geologist, you'd walk up to that canyon and just start whacking on it with your rock hammer and see what comes off. But that's not how you do rover science on Mars. You can't, take the risk of going up so close to something like that. And so it might be one of those situations where we're sort of tantalizingly close to the evidence that we want and just not willing to take the risk to go and get it, at least not for a while.
Yeah. Wow. That would be I wonder if Venus has a similar situation, because of course Venus is dry as a bone too and very hot, but we also know that it also sort of locked up tectonically, and I wonder if a similar situation happened. It took its water inside, and then whenever it locked up, it trapped it inside.
Well, it's going to be harder to tell on Venus than on Mars.
Yeah.
So let's start with the easy one.
Yeah, we send rovers to their death on Venus. Awesome, really exciting. All right, Alan, what have you got? Which one do you want to talk about first?
Let me start with the Valentids.
Okay.
There's actually a personal connection there. I know the guy who found him.
What?
Yeah, he's a director of the meteor observations at the Astronomical Society of South Africa. Basically, anybody in Southern Africa, countries like Zimbabwe and Botswana and Namibia and so on, if they've seen a bright meteor or a bolide or something, those really great ones that you want to tell someone about and reported it, you probably spoke to him. And he's not a professional astronomer. He's been doing this work and publishing papers as an amateur for decades now. And he's part of a network, the CAMS network. Basically, people are running all-sky cameras in their backyards and getting visual observations of every meteor all night. And so they're able to pick up the clusters, showers that might not be obvious. I mean, there's a lot of showers that don't get mentioned when we're doing our outreach and tell people, okay, go out tonight, you're going to see this great shower, because these might be ones that only have one meteor per hour.
Yes.
So with these these long-term observations, you can pick them up, but you'll never see them visually. And that's what he does. So this shower was originally detected in 2016. Definitely a southern view because it is in the radiant is in the constellation of Volant, which is the flying fish, very close to the south celestial pole.
Yeah, we do not have that in the northern
No,
hemisphere.
you don't. No. And then they lost it. Just didn't see it for a couple of years. And the news was that last year, approaching New Year's Eve, it came back. They found it again. And this isn't very interesting to amateur astronomers, if I'm honest, because you can't see it. It'll look just like another sporadic meteor, but it's kind of important. And it's great citizen science work, really, because what meteor showers tell you is where some large object is.
Yes.
If you don't already know about it, because I think we know about this already. Generally, it's not that there's a bunch of meteors hitting Earth. We are passing through their orbits. So something is shedding material out there, comet or what have you. And in many cases, we have identified it. I imagine Morgan probably knows a lot more about this than I do. So if there's a meteor shower and you haven't identified the object, then you know that something is out there and you've got to look for it. And then you can make the arguments about needing to know about potential impacts and whatever. So that basically is what is the value of this, is a better understanding of what is out there that we haven't seen yet.
So if I understand, then each meteor shower ties to a different object. We know that, I don't know, like the Geminids or whatever it is, tie to Comet Tempel-Tuttle. I forget exactly which one is which, or one is it Geminids or Halley's Comet? Anyway, and there are except one is like an asteroid, and every time the Earth passes through this trail of debris, we get this meteor shower, and so that allows us to better track the orbit of the object, because sometimes you go a little above the trail, sometimes you go below the trail, sometimes you hit the trail head on and you get the most meteors. And to be able to find these ones more statistically with these all-sky cameras, you start to lay down these tracks of other objects that we are passing through the trail of, that are in our neighborhood, that will allow us to better understand the movement of objects, the history of the solar system. It's pretty cool, and especially that amateurs are participating in helping to make these discoveries. I think that's really important.
It's the kind of work that amateurs are really well suited for, because what observatory can afford to dedicate a telescope to just looking at nothing all night, every night? You can't do that. But a cheap camera with a fisheye lens or something pointing up, you can build that yourself. If you've got a little bit of spare cash and a dark enough sky, anyone can do that.
Visto Tutti is mentioning in the comments that he loves bolides. That's fireballs, like bright meteors. And actually, a friend of mine just called me like yesterday. It's like, I just saw a really bright meteor. I couldn't believe it. It was crackling and moving through the sky. And if we're lucky, we see one or two of those in our lifetimes, spending time outside. I don't know if you guys have ever seen a bolide. I've seen one. It was like turned
one
green,
as well.
Green, and lit up the landscape around. So it was like a searchlight was sort of brightening like a firework going off that was like brightened everything around us, and it lasted forever. And there was like just this trail hanging in the sky for 20 seconds after the thing had faded away. It was quite amazing.
I missed a really big one in about 2004, I think. Everybody I knew saw it. I was inside.
Right.
And it was big enough that they were able to track exactly where it would have landed. Yeah. Just north of our borders. And I don't know that they ever recovered it, but they had a pretty good idea. It was picked up on seismometers around the world. It was a lovely, big one.
There you go. Nancy is saying that it's the Eta Aquariids and the Orionids are the two meteor showers attributed to Halley's Comet debris. So there you go. Yeah, it's such a neat idea that each one of these, we are passing through the trail of some object, asteroid or meteor, and then you can use that to find it. I think that's really cool. Awesome. All right, Moya, second story. Since we got all this extra time, what do you got for us?
This one is about a moving black hole in a distant galaxy. So this was in a paper that was published last Friday in the Astrophysical Journal, led by Dominic Pesce at Harvard and a team around the world. They studied 10 distant galaxies with H2O maser emission in the accretion disk. So a maser is really bright emission in the microwave. And that's why they're studying water. And that's why your microwave works, because microwaves excite water molecules. And so they studied these 10 galaxies and compared the velocities of the galaxies to the velocities of the supermassive black holes within them to see if there was any difference, because it's really hard to observe black holes moving because we can't see them. And so after they studied the VLBI data for these 10 galaxies, they found one out of the 10 that did have a difference between the galaxy's velocity and the black hole's velocity. That galaxy is called J0437 plus 2456.
Come on, astronomers. That's the best you can do.
So, I mean, that does tell you where it is. If you are tired of hearing these long strings of numbers that go with galaxy names, that tells you the position. So the 0437 tells you the right ascension. It's 4 hours and 37 minutes. And then the plus 2456 tells you the declination. So that's cool.
Right. So the location is in the name. That's actually kind of helpful.
It is. So this galaxy, J whatever, is about 230 million light years away, and the black hole at the center is about 3 million solar masses. They followed up this observation with Arecibo and Gemini, and they confirmed that the black hole in this galaxy was moving at about 110,000 miles per hour, or if you think in kilometers per second, that's about 50,000 kilometers per second. So it's moving. They don't know why it's moving necessarily, but they have a few hypotheses. One is that maybe this is the result of a black hole merger. And so after they merge, the momentum of whichever was moving faster or more massive can carry the new combined black hole and make it move within the galaxy. It could also be a binary black hole system, which would be really exciting because I don't think we've ever actually observed one of those before. And the idea here is that if it is a binary system, then the motion we're picking up on is actually just the motion of the one black hole orbiting the center of mass, but the other black hole isn't visible because it doesn't have this maser emission that we're using to observe it. And so those, we don't know which one of those it is, but I think the authors of the study have a preference for it being the binary black hole, because that would just be really cool.
Right. But I mean, if a black hole wasn't scary enough an idea already, do you know that there's one on the move?
Right.
At that sort of terrible velocity. One of the other theories that I've heard as well is that it's thought that if you get a potential merger, sometimes one black hole can just bounce off of the other one. So as they're about to go through this merger process, instead of the smaller black hole just getting consumed by the larger one, there's some way that their interaction happens that you can actually get one just get ejected as opposed to actually going in. Of course, there could also be some weird three-body interaction, I guess, that would kick one out. But it's it's kind of a terrifying idea to think that there are these objects with 3 million times the mass of the sun just wandering at high velocity out there in the universe that we can't really see until they are very helpful to turn on their maser for us.
Right. I love that it's this bright one with all this emission around it that is doing the moving, so maybe people would be able to see it coming if it's heading for their system or something. Yeah,
well, that size, you'd have a few million years of warning as it was making its way towards you before you had to sort of really panic.
Right. But 50,000 kilometers per second is fast on human standards, but is slow for motion around a galaxy.
But we do know of some galaxies that don't have supermassive black holes. The M33 Triangulum galaxy is sort of the close example of one. We've got one, Andromeda's got one, but M33 doesn't have a black hole. So I wonder if it's out there somewhere wandering.
I am writing a book about the Milky Way right now, but I'm personifying the Milky Way, which means I'm also personifying other galaxies in the local group. And that's one of the things that the Milky Way makes fun of Triangulum for.
Right. Well, maybe the Milky Way hasn't really thought through the consequences of making fun of another galaxy that's disgorged its black hole and is now prowling around in the darkness
Right.
Yeah, yeah, that's really interesting. Arjun is asking, do we know how many supermassive black holes could go rogue? Do we have a sense of how often we see these galaxies without supermassive black holes? I know you're not one of our extragalactic astronomers.
Right. Yeah. No, I have no idea.
Yeah. Neither. One for sure.
Too often.
Too often. Yeah. Yeah. All right, Morgan, give us your second story.
Yeah, so I am just constantly fascinated by like how we measure stuff. We all of science is based on collecting data, making measurements ultimately, and some things are just easier to measure than others. And yet sometimes those things that are really hard to measure are also really important. And so I'm talking here about gravity. Of the four fundamental forces, gravity is by far the least well understood from an observational perspective. We know the gravitational constant to like a couple of decimal points after hundreds of years of working. We can write out some of the other ones to 20, 30, 40, however many figures you want. For gravity, it's like 4 or something terrible like that. Yet it's also kind of maybe the most important of the forces. And it's also one that we're just totally missing a perspective on. We understand how electromagnetic forces work on the macroscopic scale. You can stick your finger in the electrical outlet and you know what's going to happen. We know how they work on the micro scale. That's what quantum electrodynamics teaches us. We know how gravity works on the big scale. That's general relativity. We do not have any idea how gravity works on the quantum or even the microscopic level. And that's where so much of theoretical physics has been mired down for decades. And one of the things that's miring it is the fact that we just literally have no data. And so this is a paper that caught my eye that I think was published in Science last week, in which a pair of researchers collect data about the gravitational force exerted by the smallest thing that we've ever done this for. And that thing is a little tiny ball of gold that weighed 92 milligrams, which is not a lot, but it's also a ton in like the quantum sense. But compared to how we usually make measurements about gravity, those things use objects that are like kilograms to the weight of the Earth, somewhere in that span. And often we're measuring something we have against the weight of the Earth to make these observations. So this technique wasn't particularly unique. They used what's called a torsion balance, which is, think of a tiny little golden barbell suspended on a point so it can rotate freely horizontally. And then you bring a mass close to one end of that barbell, and in theory, the gravity will attract it and cause it to spin a little bit. And then we detect that spin. This was actually the Cavendish experiment in the 1800s made the first ever real measurement of gravity using this technique. It's called a torsion balance because they measured the torque in the wire that suspended the barbell to make those first measurements. Today we use lasers and mirrors and other fancy things, but it's the same basic principle. You get a little thing that can be moved really easily, you bring another mass towards it, and you measure how much it moves. Then in theory, if you know how much mass you have, then you can calculate how much gravity is being exerted. The trouble is that especially when you get down to these really small things, any tiny little source of error or noise causes problems. We talk about this a lot with gravitational wave observing. But in this case, like if there was a person within a few meters of the experiment, worthless. If there was a train or a car within 150 meters of the experiment, worthless. If there was any magnetic field anywhere in the vicinity of this thing. So they did the whole thing in a Faraday cage. They even put Faraday cages between the various components to try to keep any electromagnetic forces from getting involved. This was done in Austria on a university campus. And so they waited until it was Christmas so that everybody would go home from campus.
Right, because the gravity, the mass of a person would affect it walking by.
Yeah, exactly. They pumped, it's done in a vacuum, it's done at a cold temperature, all of these things. And so they set it up with these 92 milligram weights, and they were able to calculate they were able to observe the gravitational attraction between them and calculate the gravitational constant with an uncertainty of about 10%, which is pretty bad if your goal is to measure the gravitational constant. And ultimately that is the goal, but we're just sort of not there yet. This is the first time, though, that normally you do these experiments with much bigger objects where a tiny vibration affects a kilogram less than a milligram. And so your errors go down. But if we want to understand how gravity works on the quantum level, we have to make these observations between microscopic things. And a 2 millimeter diameter 2 millimeter diameter gold ball is not microscopic, but it's closer to microscopic than a bowling ball. And so the authors argued that their technique can continue to be shrunk down as they tamp down the other sources of noise that they encountered.
There's an interesting theory that I read as well that you could, with a Bose-Einstein condensate, I don't know if you saw this as an extension to this idea. So, there's a situation where you can have a large number of particles that are all in lockstep with each other, and they act like a much larger particle. And so the thinking is that you could build a Bose-Einstein condensate and get it big enough that it gets into the regime that you could start to detect its gravity in that same way. And then that would cross the gap, because you've got essentially an object that's behaving in a quantum way, but also generating gravity at a macroscopic scale. So and once you do that, then you start to be able to make actual measurable observations of something that is both quantum mechanical and gravity at the same time. So I hadn't heard that somebody had brought a mass down to that size. That's incredible.
So this is a baby step in that direction. So the holy grail of this measurement would be to measure the gravitational effect of some object that was in quantum superposition.
Yeah.
Because then, in superposition, that thing is in multiple places at once. But gravity can only be exerted from one place. It's a vector. It's coming from one object. And so what happens when you have something that is supposed to be in superposition, but also we can measure and therefore observe, and observation is key in quantum mechanics, it's gravity. We just have no idea what would happen. And that's the kind of data that we need to be able to crack the theoretical side of this problem.
Yeah.
And actually unify relativity and quantum mechanics.
And
we're a long way from that, but this is the first baby step on that path.
Yeah, well, and as I mentioned, on the one side, you've got particle physicists making larger and larger, collections of particles in this superposition situation, and then I guess you've got people figuring out gravity experiments that are smaller and smaller. I've also heard that it could work with space-based. If you really figured this out and made this the best possible experiment, then you could then take the whole thing and send it to space, and you would then have removed all of your students walking by, cars, earthquakes, lightning strikes.
Right. Well, and the mass of the Earth is, being so close to the Earth, that's a huge source of gravity. You're trying to pick out the tiny ripples of a 92 milligram gravitational signal amongst, 10 to the 24 kilograms of Earth gravity. The farther away you can get from a massive object, the less that'll be a problem. But then miniaturizing things to work in this super fine state for space is its own set of challenges.
Yeah. And there's actually a bunch of other really interesting experiments that can be done with a thing like that, really testing a lot of the basic understandings of gravity. There's still some predictions made by Einstein that haven't been fully measured. So it would be interesting. I think that could be a pretty big priority, to build some kind of experiment like that. Very cool. All right, Alan, last but not least.
Yes, maybe least. But talk about stellar streams in the Milky Way galaxy and what they can tell us about the distant history of the galaxy. These streams usually come from galactic interactions, and if you've ever watched an animation of two galaxies colliding or seen certain deep sky photographs, you will see these big streams that get drawn out gravitationally between the two galaxies, and that's great. But there are 60 of these streams that have been identified within the galaxy, just milling around with the rest of the stars. And a paper that's come out recently has identified the sources of 23 of these streams
around the Milky Way.
Yeah.
Yeah. Wow.
Within the Milky Way. And what I found interesting was a lot of these streams used to be globular clusters, which seems strange at first, but when you think about it, globular clusters orbit around galaxies in their halos, surrounded by the dark matter and everything. So it makes sense that when two galaxies pass by, the globular clusters are going to be the first visible objects that really interact. And coming closest to the other galaxy, they can be disrupted or have stars drawn out from them, and that is basically what's been found. But not all of them. Basically, the idea is just having identified which galaxies they came from and whether it was galactic material itself from the disk of the galaxy or from a globular cluster. Not all of them. Probably about half of these have a actual identified progenitor. Others, they just know it was something from.
Was this Gaia doing this? I'm assuming this was Gaia making these measurements.
They use Gaia, well, a mixture of Gaia and ground-based observations. Gaia could give them the proper motions of the individual stars in the streams, ground-based to get the radial motions, and from there, also some spectroscopic observations to get the chemical composition to further nail down. Yes, these stars are related, came from similar sources, and what have you. I'm not sure what else to say about it, so I'm glad we put this one last.
Yeah. Well, I mean, I always find it so fascinating that we can use Gaia, I mean, in addition to charting the positions and movements of 1 billion stars in the Milky Way, that we can use this to just start to see these patterns, see these streams of stars moving through the galaxy, and know that, oh, each one of these was a dismantled dwarf galaxy, was a torn apart globular cluster. And it's such a cool idea, and that you can imagine almost like doing archaeology, that you start to roll back the Milky Way's process of formation in time to understand what it, first it ate that, then it ate this, then it ate that over there, and then it gobbled up this. So, all right,
I was going to say that some of the streams share a source. So you might have one globular cluster forming two separate streams, or a stream which has since disrupted and broken apart. But well, that was just an extra detail. Yeah.
Well, you're on my screen right now. We're reaching the end of our hour, so why don't you let people know what you're working on and where they can find out more, Alan?
Okay, well, I continue with the Astronomical Society of South Africa as working in the citizen science section. But I think you're more likely to find my work on the Urban Astronomer podcast. There's been a bit of a hiatus for a while. I think, lockdown blues and all that has made it hard. But it's still out there, still getting downloads. And it's urban-astronomer.com, and just follow a subscribe link.
Terrific. Moya.
Hello, you can find me on Twitter at GoAstroMo, and right now I'm gearing up for my dissertation defense, which I know is in 20 days because I'm counting down on April 6th.
Right, so that's taking up a lot of your mental space.
Yeah, it really is.
Defend. Morgan,
Defend.
Morgan, any tips?
If you got to this point, you're in good shape. It's all easy from here.
Thanks.
And Morgan, what are you working on?
I've got some cool stuff that's been coming out on SciShow. I was editing an episode a few weeks ago about these new NASA program called Astronomical Pioneers, or Astrophysical Pioneers, which are these really small scale, like $25 million missions that are testing out cool new ideas in astrophysics. And so I don't know if that one's hit yet, but it'll hit relatively soon. And you should check it out. There's some really neat stuff.
Terrific. All right. I'll put us all back. All things universe today. I had a couple of really interesting interviews this week. I'm sort of making my way through the NIAC award winners and showcasing what they're working on. So earlier this week, I had a conversation with a person working on the Lunar Far Side telescope, and this is building a radio interferometer on the far side of the moon to peer into the cosmic dark ages. And I had another great conversation yesterday with UCLA professor Ben. Oh, I forget his name. Anyway, we talked about building giant interferometers and some other really cool topics that a lot of people will really enjoy. So I'm having a lot of really fun interviews on my YouTube channel. All right, let's bring this all back here. Put you all back on the screen. There we all are. Thank you, everybody, for joining us this week for the Weekly Space Hangout. We really appreciate you joining us. As always, a huge thank you to all of the moderators and all of the Weekly Space Hangout crew, and a special thank you, as always, to Nancy Graziano for all the hard work that she does behind the scenes. We really appreciate it. So thanks, everybody, and we will see all of you next week with a guest. Thanks, everyone. And press the button.